This video is going to discuss the quantum mechanical model of the atom and quantum numbers. We ended the previous video with the Heisenberg uncertainty principle, which said that we can't know the exact location of the electron, so that really shifted the way of thinking for chemists. A scientist named Erwin Schrödinger developed a mathematical model that took into account the wave nature and the particle nature of the electron and started to determine these probability diagrams that help us to predict where the electron is located. An example of one of these diagrams is here. The dense areas of the diagram are areas where you are more likely to find an electron. This is known as quantum mechanics, where you're using probability to predict the location of an electron. This is a shift away from the Bohr model. The Bohr model put electrons going in circular orbits. The quantum mechanical model says the electrons are located somewhere in this region of space. They're moving very quickly, but we can't say exactly where they're located. So scientists were able to solve a series of wave equations to determine regions of space where the electron was most likely to be located, and we call those regions of space orbitals. And they were also able to calculate the energy for each orbital. So an orbital is a three-dimensional region of space where an electron is very likely to be located. We use a set of numbers to describe each orbital, and these numbers are called quantum numbers. For comparison, let's consider a sporting event in a major stadium, and you're trying to find your seat. You're going to be given a series of numbers that describe your seat. You would be given a section number. Within that section, you'd be given a row number, and within that row, you'd be given a seat number. Quantum numbers work very much the same way within the atom. They're going to give you an energy level, an energy sublevel, and then an orbital. So it's a series of numbers that describe where the electron is located within the atom. The first quantum number is called the principal quantum number, and we use the symbol N to represent the principal quantum number. This describes the energy level where you would find an orbital. We talked a little bit about energy levels when we looked at the Bohr model in the last video. Electrons can be located here on this energy level or here on this energy level, and they are represented by the symbol N. So that's kind of introducing quantum numbers. N represents the energy level. It's going to be an integer or a whole number. It's going to be 1 or greater. Our second quantum number is called the angular momentum quantum number. We use the letter L to represent it. And this is going to define the shape of the orbital. So I'm going to show you 4 different orbital shapes, and each one has a different value for L. The first type of orbital is an s orbital. These are spherical in shape, and the value for L for an s orbital is 0. So the quantum number information would say L is equal to 0, and that tells you that it's an s orbital that is spherical in shape. The radius of the sphere increases with a larger n value. So recall that n is the energy level. The higher the energy level, the larger this sphere is. The second type of orbital is a p orbital. You can see the shape here. A lot of times this is called a barbell shape. There's a node in between, and a node means an area where you will not find an electron. So there's this area of empty space in between. The value for L for a p orbital is 1. So if you see L equals 1, that's telling you that you have a p orbital. Also notice that the p orbital can be in 3 different orientations. If you think in terms of a 3-dimensional axis, it can be on the x-axis, along the y-axis, or along the z-axis. So you see 3 different orientations within the p orbital. The third type of orbital is a d orbital. You may have noticed that the shape of the orbitals is getting more complicated as we add each one. Most of them have this clover shape to them, but then you have this one that's an odd shape that is still considered a d orbital. The value for L for a d orbital is 2. So if you see L equals 2, that tells you that it's a d orbital. Most of your d orbitals have these 4 lobes with an empty space in between them. One of them looks like a p orbital that has this donut shape around it. The final type of orbital is an f orbital. The shapes for these get very complicated. There are 7 orbitals within the f sublevel that we're talking about, and the quantum number L would be equal to 3 for an f orbital. So the values for L are 0, 1, 2, and 3, and they represent s, p, d, and f orbitals respectively. So L, which is the angular momentum quantum number, tells us the shape of the orbital, tells us whether or not it's an s, p, d, or f. Allowed values for L depend on the value for n. L can be from 0 to n minus 1. What I mean by that, suppose an atom has a value of n equals 4. It has 4 energy levels. L can be 0, 1, 2, or 3. If an atom has 2 energy levels, n equals 2, then L can only be 0 or 1. Recall that earlier I said that a p orbital can be along the x-axis, the y-axis, or the z-axis. So there's 3 different orientations where a p orbital can be found. So there is a quantum number that describes the orientation of the orbital. This is called the magnetic quantum number. We use the symbol m with the subscript L to represent that. The magnetic quantum number describes the 3-dimensional orientation of the orbital. The allowed values depend on the L value. So if your L value is 2, then your magnetic quantum number can be anywhere from -2 to 2. It's going to be integers, but it could be -2, -1, 0, 1, or 2. For any energy level, there can be 1 s orbital, 3 p orbitals, 5 d orbitals, or 7 f orbitals. Let's look at some examples for this. If you take for example the first energy level, n equals 1 is your principal quantum number. Your second quantum number, the angular momentum quantum number, was represented by L, and it can have values that go up to n minus 1. So you see that here. If n equals 1, there's only one possible value for L, and it's 0. If n equals 2, L can be 0 or 1. If n equals 3, it can be 0, 1, or 2. And if n equals 4, it can be 0, 1, 2, or 3. So L can go up to n minus 1. M sub L, which is your magnetic quantum number, can go from -L to L. So if L is 0, M sub L must also be 0. If L is 1, M sub L could be 1, 0, or -1. If L is 3, M sub L could be 3, 2, 1, 0, -1, -2, or -3. Think a little about what this means. If L equals 0, that's an s orbital, and there's only one possible arrangement for the s orbital, so there's only one possible value for ml. If L is equal to 3, that's an f orbital, and there are 7 different arrangements, so you see 7 different possibilities for your m sub l value. The picture we looked at the most was the p orbital. P is represented by L equals 1. We saw 3 different orientations where that p orbital could be, so we see 3 different values of m sub L. Each one of these quantum numbers gets us a little closer to describing the location of the electron. You have an energy level, then you have a sublevel, and then you have the different orbitals within that sublevel. Some other terminology that you very commonly see: electron shell means everything within the same energy level. So all of these are in the same electron shell. All of these are in the same electron shell. The different types of orbitals are often referred to as subshells. So these L values represent your different subshells. S, P, D, and F are the 4 different subshells that are available.